seems that I just sent you a request to start.
Yeah, it's recording.
Oh, nice, nice.
Recording.
Perfect.
So I guess I can stop this guy.
Yeah, definitely.
Okay.
This desktop doesn't have any microphone, right? But it should be, this desktop doesn't have any microphone, right? But it should be fine with the microphone of my mobile.
Yeah, it should be. Okay, so we had some luck yesterday trying to get, this is the end graphic that was that we obtained, and as a part of, again, this auto reporting pipeline, the data for this sweep and also the final renders, they're both captured in the output directory. So as you can see here, the best step that we were able to get, we did get gradings on some of the cores, so but we can work with that. This is like already good enough for us to continue. Step 6,616, which if we open the actual data being collected, that puts us here. So those are the corresponding image coordinates for that very specific step. So we know that, like, as long as we don't touch the camera, we can get back to the state by moving it to that specific coordinate position. And which is what I've done a little bit here. I've kind of, it's not exactly the position that we were at, but we can move it to that position by so we'll know I'm doing yes. Okay. This will have to do. A little bit more reasonable. But so if we look at the current position, we're about like 60-ish pixels off in the X direction, and then right on target for the Y. So what I'm gonna do is you can use cursors for this. It's pretty helpful. But I think this will just, you'll have to kind of try and see how each of these legs move. We already have gradings, but I'm just demonstrating how you can like move to a target position. So that puts us pretty close in X. .692. We're currently at 644, so 50 more pixels in Y, which puts us approximately like here-ish with the yellow cursor. Wrong one. while you're scanning this, you might come across, already really good gradings at some point, which we've, for example, gotten here. This is already good enough, and we can proceed with the next step, which is to optimize this a little bit. So regardless of, even though we have really poor, like the cores are not being coupled correctly, we can correct for that later. But right now, I would like to optimize for this a little bit, so that for this very specific coupling configuration, you get the best signal that you can. This again, this is like just approximate. Okay, so once that happens, you can actually take a look at the core, and what cores are actually being coupled. You can do that just by disabling, readings from each core. C is coupled, I is coupled, J is not coupled, A is not coupled, U is coupled, and B is coupled. So we're actually really close, and this just means that only J and K are not coupled. If we take a look at this grid search reference, if J and K are not coupled, that puts us at position 3, which is here. So we just need to move it to 0. And the way that you can estimate this distance is just in this image. Let's just say that your current position is this yellow cursor. You just need to move it up by 1 core, which puts us at where the red cursor is. So just move the center core up to that position.
But what is on the number 3? Is this the center core that is on the number 3?
Mm-hmm.
And
Yeah.
you need to move it on 0?
Yes. And you move it up, and you need to move it onto 0. So another thing that I will mention, that this arrangement is very insensitive to the orientation of your entire system, and sometimes for mechanical design purposes, they will just like change the orientation of the camera. So depending on what setup that you're actually, so like for example, for the 5-bar, it used to be like this, but since we've changed our rotation, it's actually now this. It's just something that you experimentally sort of figure out, like, oh, it seems like, this thing's rotated.
So right now it's gonna be always like in the perfect order, like that, and not rotated. Is it gonna be always aligned to the rotation, but not in X and Y, and you need to look on only X and Y? Or you?
What do you mean?
Yeah, like for example, how do you know if it's not rotated? Like what you said, like a little bit like this.
Oh, that's clocking. So clocking is something that we control for manufacturing.
Yeah, there's no solution to that here.
Okay.
If it's clocked.
So you're assuming that it's not gonna be clocked. Okay. And
It
how
is.
do you make sure about that? Like about when reading the signal, if I try to do something here, and I can match and get signal to every core, that makes it the fact that it's rotated and locked. We need to get it back and do some experiments in order to fix it, or there is a process in when you are building.
When I'm building, if it's badly misclocked, I should know.
Okay.
And
When that system gets to this system, when the free space connector comes here, it should be fixed.
It should be, yes.
Okay.
I guess, the puck also has an effect on that. So
Okay.
And, if there's a problem with the clock, if it's not maintaining clocking properly, then, that may happen after, that should not. Mechanically, it's not supposed to.
If it's improperly clocked, your center core will align, but the outer cores will be rotated, so you'll get a high signal on the center core and you'll get crap signal on the other cores. So that would be the indicator that you're incorrectly clocked.
Yes.
But there's no correction for it. It's a manufacturing defect.
I see.
If it's 90 degrees or 180 degrees or something, it's probably something combined of the X-Pack.
Good to know.
So yeah, just to like kind of tag on to what they were just saying. So you can imagine there's two fibers, right, that we're trying to, and they have to geometrically align. And if either of them are clocked, you're not going to get coupling. So the system side of the hex pack is something that Chuck controls for in manufacturing. So if it comes off the line, we can assume that it's clocked right. So unless something came loose and is like completely screwed up, that should hold. However, there's the sensor side, which, well, first of all, our camera is actually looking. So if it's like very severely clogged, you can actually see it on the. You can actually see it on this image. Is that this
Right.
geometry is like off, right?
So there should be always a line, right?
It should be upright. It should be like that, unless there's some weird camera configuration that we're doing, but we're not doing that. So like Chuck said, the main symptom of clocking, if you like disregard the image and you just look at the gratings, is that your center core is really well aligned, but all your others are like weak. However, that could also be magnification because we're actually magnifying and then focusing the image back. So if you have a magnification kind of like discrepancy, you could be correctly clocked, but then like all your outer cores are like way out there, and you still wouldn't get coupling. So it would show up a very similar way that clocking would. But what was I going to say? This is all stuff that we sort of catch if we like use our ferrule press station correctly, because like previously when we were building the sensors for these setups, they're very precisely pressed, and then they also have a rotational correction mechanism for that as well. But by the time the sensor gets into the puck, the clocking should not change. Okay, and it should just stay there unless something terribly goes wrong. Yeah. So now we were just moving this up to that other position, that estimated position. It's gonna go out of alignment for a second. And then yeah, here it is. These are all the cores coupled. I will point out, as you're aligning, you can also kind of tell like where your center core is being coupled, because of our fibers assembly geometry, and also the gratings that we put on the center core instead of the outer cores, they look very different. This is like an outer core, and this is the center core. Okay. The spread between max and min is a lot smaller for the center core, so you can actually use that as another piece of information. But I see. Basically, for this, my main goal is to actually, because the peak find is so off right now, I'm going to be let me get the camera position first. We're still exactly where we need to be. Oops,
Screen sharing, yeah, the one that he showed.
Although, is that a window or is that a?
Used to it being, yeah, outlined green. I was wondering if it's different windows.
Oh, I'm sharing the whole screen. So let me double check. Yeah, it's showing.
You,
Okay,
you
it's showing.
shared it, yeah, properly.
Yeah, it's showing. Okay. But basically, from here, you just want to kind of take incremental small steps, treat them as individual axes, and just like optimize them one by one. Kind of like just play around with it. There's because each actuator behaves slightly differently. There's no like tried and true, like the magnitudes that you have to put into these steps are all going to be very similar, but like you can't like the actual movements that correspond with each move like on the image is not doesn't stay the same all the time. Okay, so now that we have coupling in X and Y as well, what I like to do is let's see. So unfortunately, this time we have a really poor image because we're using a new puck and it doesn't have all the anti-reflection pieces to it. But we can sort of still see our image, so we'll just work with that for now. Make this hard to get.
Can you say it again? What was the name of that?
What's that?
What was the name of that?
So see if that other.
So here. So as you can see right now, our image is kind of washed out by actually taking that lid off, something just moved. I would say at this moment the pucks are pretty prone to rocking around, so like just be careful when you're handling the pucks. You can easily bump it out of alignment.
Okay.
But basically, you see this like little black piece of tape here. That's an anti-reflective tape.
Okay.
So right now, as you can see from our image, we have a really strong background gradient, and part of that is just lightness, because the way that this works is that you have your LED on the system side, and it has to travel through a light pipe through a gap and then reach the end of the fiber. So, but right now what's happening is that the light, when it's reaching this gap, it's actually bouncing around this gap here. And that's what this is supposed to mitigate. And we've proven that it does, but the puck that we have on there right now doesn't have one of these.
I see.
It's just something that we'll have to, because like eventually we might use a different material for this that's already anti-reflective or some other thing. But that's all like stuff that I guess Sam is helping us figure out. So at the moment we have, with this current camera configuration where the camera currently is, basically our reference position, which we can get by just clicking correlate. Again, the image correlation is not at its best performing right now because of the lighting conditions, but you can, this is the general region. And then what I'd like to do, I haven't done this for any of the W units yet, but if we had our auto alignment procedure,
Can you tell me what's the meaning of this image? I mean, is it correlated, but the final output of the correlation, but what is the purpose of this? To see a finer image, like a more, I mean, a sharper image or something like that? Or?
no, this is just to tell you how well your find is,
Okay.
because for this is just because what this is a whatever your final coordinate is, it's just getting a crop around that, and that's the image.
Okay.
So basically what I use this for is, like, for example, there's some like weird artifact or reflection here, and instead this finds that, like, you can see if it's actually looking at
the fire.
if it thinks that it's actually looking at the end face, because
Mhm.
it will go and latch onto something else. That's something that I think will need to be fixed, and I have been writing about that. Now I was going to write the, so if I had to, if we had our auto alignment procedure all written out and implemented, what would happen next is I would create a copy, or could create the copy, what's this build? Pre-space connector W1, build 4. And then I wouldn't change anything else except this target position here, which is just this guy, 1467 and 7. Okay. So previously for the M units, what you would do is you just take this connector setup step and just upload that very specific, like this guy, and then just say like, oh, upload and update your params, and then force load the configs, and then you can verify on the server's logs that the name values have actually been changed from whatever the previous values were to the new values. So if we had automated alignment implemented, now we should be able to just run an alignment. However,
Okay.
since
So,
we don't have that implemented, we can't do that.
so basically, this one gets created automatically when you push a specific button, like create.
So this
reference
guy,
image.
so as I mentioned yesterday, right now we use a generated reference image, so which is just an idealized version of what that reference image is. But an alternative way you can actually do that. So again, there's two methods. The alternative way is to basically just get an image, like a live image, and then just like crop what the end face looks like. So, and it's used for our image correlation algorithm. So it's basically just taking what you're trying to find and then laying over like a million times and then see where the response is highest. So it's just, you just need an image of the end face, and so that you can find. Again,
My question is more like, at what time is created, so I can come here back again in this tab and then pick this specific image that I got generated from.
yeah, that generated reference is, you can use it for anything. There, like, this generated reference image works for every single connector. Is that?
But who created who created that? Like, is the out
There's a separate VI for that.
exactly?
There's a
That's
separate
my
VI.
my question. Like, who created that image reference? If there is a specific PI, when should I use it? When I am just calibrating and trying to find the best spot and then hook.
It
Take
it
the-
doesn't matter when you do it. Like you can generate that at any point. So
Okay.
this reference image is not generated relative to any of our data, any of the data that we collect. It's completely agnostic to the connectors. It's just a 2D image of what the end face should look like. And I'll pull up the VI. I'm not sure I know where the VI is right now, but I'll find it. I'll dig it up. But the only time that you'll have to generate a new image if there's a significant magnification difference. So like if now the system that you're using,
I see.
the end face is like 400 pixels wide, using a 50 pixel wide reference image is not going to be able to work. So you would have to like generate a new reference image that matches the geometries of that. Okay. I'll dig up the VI for that and then make sure that's documented. But yeah,
Okay.
does that answer your question? Okay.
And this one is just the connector params from the sensor or I think it's the free space connector, right? These params.
Yeah.
Connector param path is the one that you created as a copy, right?
Yeah, it's that text file.
Mhm.
However, you might notice that our registration fitness is actually absolutely terrible, and it's because we're not loading the right cal file. This sensor is 104472. So what I'll do is, as another step of verifying that the shape actually works, I'll load the actual sensor file.
The sensor file in the MCF5.
No, this is in our manufacturing repository. So every time that we manufacture a sensor, it
You
comes
get the
with
calibration file.
you get a calibration file that comes with it. There are utilities that people develop to help you find the cal file for a specific sensor. Like for example, usually the sensor number is just over here. There's this one util called dude, where's my cal? And you just put in the sensor number, it's going to give you the output path. So I would say, like, if you have to find a sensor file, just use that.
Okay, great.
Uh,
This is provided by UAL, the FSysCon
yes,
spec. Okay.
yes, it's currently in the SVN repo, but if there are any updates that you need to make to that, talk to Joel about it.
Sure. And the CSV is the one that you built when you were testing the Delta robot, and you created that lookup table, right?
This was generated from the MATLAB the MATLAB kinematics model. That testing was to verify that the model is good enough for what we're trying to do. So that testing didn't generate anything. That testing was just for us to like see what the output angles are for each of the 5-bar joints, and then confirm that like yes, we can actually use the ideal model that MATLAB did.
Okay.
Yeah.
And the MATLAB kinematic models is stored in SVN or?
Yes, those are all there. Yeah.
Okay. There is nothing built yet for the Delta robot that is currently being used, right?
Yeah.
That needs to be built.
So again, like that control schema is completely going to be very different. I think this is a useful reference for how to like for example, model something and then generate into like a lookup table. So use here, but you're probably going to have to rewrite basically 100%.
Okay.
Yeah.
Okay.
Who is doing that modeling?
Me. For the 5-bar is a fairly straightforward mechanism. There are articles online written about it, so I just copied the equations there. But for the delta, I would say talk to Graham about it, because he's
Can you
more-
point at the folder where is located the current simulation of the current kinematics of the?
There's a Confluence page seconds
Okay.
in that team.
Sure.
Yeah, it's in that big it's in that big
It's in
list.
that. Okay. Okay.
Yeah, yeah. So now that we have the right sensor cal file loaded, actually try and see, and we get really good registration fitness, like really, really good. So
You say that it's really good because you need to be the closer as one.
Yeah.
You need to be
Yes.
close as
Yes.
as
yes.
you know,
So
the closest as one.
So generally, if you're looking at registration fitness or you're trying to interpret generally what that means, anything above like 0.8 is really good.
Okay.
You can make shape with it.
Mhm.
And it's a continuous spectrum, right? There's no hard cutoff or anything like that, but it's just indicative of like generally where we are. And so what I'm saying is not like coded into the logic, but it's just general rule of thumb for me. Anywhere under 0.3, so like 0.1, 0.2, either means you're not coupled at all, or you're coupled onto the wrong pole.
Okay.
So, because that has to match exactly the mapping that you have in the sensor cal file.
Hmm.
Anything above like 0.3, all the way up to like 0.6, just means that you have coupling and you're using the right cal file and you're using the right cores, but the signal's just not good enough. Signal to noise ratio is really bad to the point where the shape sensing algorithm can't use this. It's probably going to give you a lot of errors.
Okay. There is no way how to troubleshoot that.
So that would just be so that's like a lot of the actual shape sensing and optics stuff.
Okay.
And some of the main causes for free space connector can be like, oh, your reflection is really, really bad, and it's raising your noise floor too much to the point you can't resolve for the actual peaks of that, or your grading amplitude is just really poor. Like you can be like barely coupled, like in terms of your cores, it can be like slightly off, and you can think of it as like just you're overlaying two circles on top of each other. Like the more that overlaps, the better your signal is. But if you like even move it off by a slight bit, like a micron, or in our case, like actually a micron or 2 microns, you lose a significant chunk of your signal. So this looks really good, but this is not an absolute verification of like, yeah, we can use this. This will yield error-free shape in our setup. What I do, what the usual method is to go to applications.
So you show it here.
Oh yeah, to go into like our actual Contour app, which is not a free space connector utility. This is just something that
Just a Contour.
this is part of Contour, and run it here to see how we're doing on all of our error statuses. And for the most part, generally what we consider as a successful shape is if the sky is okay. And right now, as you can see, there's still like, this is more just into general shape debugging. But I suspect this one is potentially, and you can see from Contour, you can actually like see the shape now. Like it's live rendering the shape of our sensor.
Yeah, it's really nice.
But this is still giving us errors. And if I had to guess, it's probably because of that big peak we have at the connector. So this guy here, it's probably creating some issues. Right, so sometimes it'll go okay, but if I had to guess, this setup here might also be like twisted or something.
So I pulled it out.
I see. Yeah. There was probably a little bit of contact stress on that as well. Still errors, a little less maybe, but yeah, this becomes then mostly like, you know, how do you actually debug a free space connector and like what shape actually looks like. If I had to guess, again, this partly is maybe because of this peak that we have here. It's raising our noise floor. One more thing that I'd like to run through is like for like especially when you bring up a new free space connector, we got lucky here in that the connector location, so all the optical components that you have here all have more or less this similar length, such that our peak finding algorithm was able to latch onto this guy. But sometimes when you have a hex pack that's slightly longer, slightly shorter, or something like that, it actually creates enough of a path length difference such that our registration can't line up. So I'd like to run us through the process of like actually doing a connector locations find manually. We don't have an automated algorithm for finding connector locations yet. That's something that we have for us, like our different systems, but not for this because there's a lot of peaks here, and the optical network looks very, very different than the normal setup. So what I do is I go into system diagnostic. And if your system's running and you just run connect, it automatically detects the state and just knows that it's running. But you can go into here and toggle all these guys, bring down the filter a little bit, and then basically what we're trying to do is read the exact the exact time delay value for this very specific peak. So this is the peak where it's the connector interface. So this guy here. What I do usually is just I note down every single. I'll just actually do it, but I have a piece of paper or something like that here. Here, I'll just do this. Posted. Don't put too much use. I'll go with you said. What I do is I go through the S channel for each of the S channel for each of our 6, 0 to 5, and I just note down basically the peak location. It doesn't have to be super accurate, but it shouldn't be too lousy-eyed. So for this, I'm just going to say it's 25.9.4, 0.904, 25.899, 25.893, 25.890, 25.891, and then 25.894. Okay. So now that I have these, I'm going to go into, I'm actually going to stop our shape sensing for now, and then go into this and see if I configuration and actually edit the fan out connector location for each of these, and basically just use the values that you just wrote down. So I will, once these are all updated to the values that you just got, save to MCFI, then we can try starting this again.
So you're doing this because of that concept, right?
Hmm?
You're doing this because you want to troubleshoot the.
No. So sometimes what happens is that you have the right sensor, you have good coupling. But if you look at, but your registration fitness is really poor, and the registration is basically the analogy that Brian always uses, is that you basically have like a fingerprint of what your sensor should look like, right? And then you have your CAL file. Oh no, the fingerprint of digital fingerprint of what your sensor should look like, which is your CAL file, and you have your actual readings, and you're trying to line them up in delay space, time delay space. And there are times where it's just off and it can't find it, and that shows up. That's basically the registration fitness tells you how well the current readings are fitting to the expected reading, basically from the calibration file. And sometimes you'll see that the registration fitness is really low and the registration offsets are really high, even though you can clearly see that you have gradings and everything. And sometimes that reason is because the path lengths of this new connector that you just put on, that you just installed, the free space connector, is slightly different from the previous one, such that you basically have to like reset the path length assumptions for your entire algorithm. And we do this for our current systems anyway. So every time we install a new jumper or replace any like cabling, like for example, the standoff or fan out or anything, that all changes the path length of the system. So we already have to do this for our current system anyway. It's just that we have an automated system for that, but here we don't have it yet. It's something that I think would be really helpful. Should be done automatically, but it is currently not. And usually you can clearly like, I would say like just as a general rule of thumb, like if you're off by like anything in like the second decimal digit or the third, the algorithm should be able to recover that. But if you're off by more than that, then definitely you'll need to update the connector locations. So, so yeah, that's that. So now we have shape, and we have a working CAL file that has already been uploaded to the MCFI because we did this.
After you got shape, and in previous versions, did you used to record any sort of value, like what values would you be interested to store in a CSV file in order to show the team that it got signal properly?
Well, I mean,
or what
you
else
can.
would you-
So I think some values that are right. Thank you for bringing that up, because there's another metric that I didn't mention. So usually like registration fitness, grading amplitudes are good measures. And then also one thing that we should briefly talk about is we actually didn't have a unified loss metric or a SNR metric until very recently. This is something that Chuck Jarrett developed. So I would say talk to him about standardizing your SNR measurements for every investigation that we do. But this VI apparently just it gets live data and you get SNR off it. So this should be our golden standard, not golden standard, but metric, unified metric for evaluating poly connectors too. Because
is this evaluating it through time? Like,
No, this is just a snapshot metric.
okay,
So like, if you just take a screenshot of this and send it to people, they will understand what that means. I would say that, like for example, things like registration fitness, they saturate out really quickly, as in like you could be slightly off and you could have less than ideal coupling, but still get really good registration fitness. Grading amplitude is entirely MCFI dependent because of the laser output power on the MCFI. So like this, right now we might be getting, like 6-digit grading amplitude numbers, but if you put it on a different MC5, it could be 7 or 5 digits, and it would be the same connector, same connection. So it's completely dependent on the MC5 that you put on. But the SNR, signal to noise ratio, is basically just taking the amplitude of your like a segment of the gratings that you specify versus some noise, and then well, it's a ratio, right, between that. So like we should be using a unified metric for it.
and
This is also how we know, like, because every time that a connector comes off of the assembly line, or Chuck finishes assembling one, he will take data on how it performed with the golden sensor that he had, and then a lot of times we'll want to know how it performs on a bench with our setup and with like a non-golden sensor.
and for the thermal drift, and it's like the same thing. Like you used to get those older values and store
So-
them, and you just log them to time.
So
Maybe 1 minute, 1 hour.
So for thermal drift is a really tricky problem because, so I will just say that, like, for example, if you start off at room temp and then you ramp, you put this in a thermal chamber and you ramp it up to like 60 C in, let's say, like 30 minutes, or you wait for it to settle, you're not going to get shaping. You're just not going to get shape anymore. And that will happen even at like a delta of like 10 C, which is why we need like an actual like tracking system that tracks the gratings as it kind of diverges from your initial configuration.
For this version, it's not yet right. It's not developed yet.
Yeah, it's not. But yeah, we did a good amount of thermal testing on this. I think it will be very similar for that, because everything in the system deflects when it comes to like thermal drift. Like everything from the lens holders, the actuator itself, the actuator mechanisms, and also everything from like the puck that's holding the sensor, that also deforms. And then also like your camera mounts, the camera itself, like all of that drifts. So it's really hard to like nail down a single piece that you can like individually track, because whatever system that you're measuring these deflections with will also deflect if you put it in a thermal chamber. So a lot of it is just like, we just need to make sure that you're clear about the objectives of the system, which is just to track readings. Like all the free space connector needs to do is to be able to get gratings when you put on a new sensor, and then be able to hold that gratings for however long. So that's why we need that like low speed correction. But you don't actually care how the camera actually drifts. You're just using that as a heuristic, but it's still useful to make sure that your heuristic updates with the rest of the system so that you can still use that heuristic down the line. But if that makes sense. For vibration testing is another piece of another big piece of environmental testing that we do, and we have a shake table for that. Joel has been doing pretty much, I don't know, it's either Joel or Chuck has been doing all the vibration testing for that, so I haven't done any of it myself. what else is there? And then another piece of testing that we do is uh, like the kinematic mount testing. So like given a piece of given a single sensor that's like sitting in a mount in a puck, like just pick it up and put it back on like a lot of times and make sure that the position that you end up with is exactly the same every time or close to being exactly the same because that's a requirement of the kinematic mount or what it's supposed to be designed for. That's another set of testing that Megan we drives and I just support. But the last piece is like just general repeatability and integration testing. So, which is what we did last year for CIP, where you just take like what we did was um, we had 10 of these endoscopes. We had 5 this different unique free space connector units that have been built and calibrated and all of that. And for each combination of endoscope to catheter to endoscope to free space connector, you make that connection 20 times. So all in all, you have 8,000 total connections, and that's an evaluation of like general how good people design is, because then that means you have a spread of endoscopes or spread of your sensors that work on a spread of connectors repeatedly. So
Do you know how to plug in the endoscope?
So this is specifically built for again that free space connector design.
Okay.
So this is trash, right?
Okay. Okay.
But eventually, you'll have a different endoscope design
Okay.
with
Okay.
the current sensors integrated.
I was wondering if this is something like it was like normal standard.
Well, I mean,
used in the final system.
repeatability testing and the general concept of like just taking catheters and putting it onto the free space connector, that's like very high level, and I expect that's probably still going to be the case. But what the endoscope looks like, or what the carriage even looks like, is probably very. Yeah. I don't know if I can find a lock carriage, or we still have that guy. So this is the block carriage that we did for this testing. We'll probably have something very similar, or just on an actual fin. But what we did for the longest time is just, while we're doing this repeatability testing,
Just putting it on top and that's it.
and that's it, like that.
Right.
And then you click start, and then
Interesting.
what it should do is it should just align.
Okay.
Take it off, do it again with a different catheter, and then once
Inside that thing, there is a
There's a sensor.
sensor.
there's a sensor in here, and you can see that this is the puck integrated into the rest of it,
Nice. Mhm.
and the free space connector is actually mounted in here.
Okay.
That the thing that's mounted in here is one of those guys.
Okay. Mm.
Yeah, but
Good.
Yeah.
Good. I didn't know how you used to use those guys.
yeah, this is like that's how the free space connector should be used. Although the like there's okay, so I think just the vibration of the bike has something we don't have as with hopefully anymore. But but yeah,
Yeah.
that's setting a unit up, and for the most part, a big part or a significant chunk of my day to day for the past couple months was just like every time a new build, a new assembly came out, test this. So it's just like bringing it up and everything. So,
Yeah. There are a lot of things to be aware of.
yeah.
Just- Just one last two things, if it's possible.
Sure.
First of all the C++ code that you were maintaining and things like that, when you do an update, you need to load them into the NCF5, right? You need to send those files into the
So
the
so
RTOs.
basically, so because we're using Samba Share, so which means that you can actually just, at least in Windows Explorer or even PowerShell, you can access the certain directories on that MC file as if it's just like a folder here. So what you could do is just like you can work on the MC file directly, and that's what I do right now. So when I have, when I have this open, this is actually just the source files on that MC file. On the MCFI.
I see. That's
And
nice.
the NCFI itself already has CMake and everything in a build environment so that you can just build on that MCFI.
Oh, perfect.
So you don't have to like, build on a separate build
Exactly.
environment and then send that
Exactly.
over. Just edit the source code on the MCFI directly and then build it there.
Nice.
But
Yeah.
just, so that also means like you can just do all your Git operations on that as well. So
You know how to set up that, right?
Yeah.
I would like to, want to shop on that.
Mhm.
And yeah, the other last thing is, can you restart the system from scratch again just to record? I mean, because you thought that yesterday, but yeah, I would like to record it. Like, I mean, for example, why do you have two NCFIs? Is it the reason?
Oh,
Are you using only one or?
yeah, so this MCFI is for that setup.
Ah, okay,
It's
okay.
over there. This is only. I will say that this MC5 is slightly different in that it's M17P
Mm-hmm.
and it has this guy exposed.
Mm-hmm.
And what we use that for is actually ranging collimation, ranging collimator. So you can use that as almost like a instrument measure distance.
To measure what?
Distance.
Okay.
So the ranging collimator works. It's basically, I don't think I have one here, but it has just slight like what you'll plug into that is just a connector, and then it'll have some length, and then it'll just be like a little tube,
Mm-hmm.
and you can mount that tube anywhere, and then light will come out of it, and then reflect off of it, and come back. And just based off of that, you can actually measure what that distance is. And we've been able to achieve like sub-micron level measurements with that, which is actually really, really nice. And for the longest time, we had collimators integrated into our free space connector because it's a good measurement.
No.
It's an absolute measurement, but we can't actually use it in product because we can't use M17P MC5s in our product.
So
in
you
the
were in
products.
charge of maintaining that code and
So the ranging collimator, so you can actually, there's some utilities already embedded in this BI, just the ranging stuff here. There's nothing connected onto that channel, which is why it's all garbage right now. But I did a little bit of work with this, but Joel has done most of the work with like setting up the.
Okay. So he knows.
He knows
He's
all
good.
this. He knows
On that level.
everything. Yeah.
Mhm.
And then there's like usually the one MC5, one M17P MC5 can only support one ranging collimator.
Mhm.
But you can actually Joel had an artifact made which splices like 6 collimators together, but at different path lengths. So instead of having one big peak on a single channel, it'll be 6 equally spaced out peaks. So you can actually like mount 6 different collimators and do that with that MC5. I had where's that other? You can see I had these like really high reflection mirrors mounted on top here. Those I used to use as targets for ranging collimators.
Mhm.
So what we did for this Delta setup was like I wanted to measure the positions of each of these linear actuators and also the XYZ position of this, like, of the effector. For the Delta or any of the actuators that we build, if you can, ranging pollinators are a really good way of measuring, especially like any winter crop. That's why we have that MCFI here, but right now it's not hooked up to anything. I can just run through, powering
Yes,
on
just
everything.
the powering. Yeah.
So
yeah.
I'm not going
Because
to disconnect anything on.
Sure.
the
Exactly.
speaker, but
Exactly. Exactly. Yeah. Just powering it then.
That's fine.
Mm-hmm. Because I saw that you opened a session of Woody.
Yes, yes. So I'll just power everything down, and clean up a little bit.
Sure. Sure.
Uh, okay. So now that it's stopped, I'm going to kill this putty session as well, just so we can start from scratch. So I'm going to start the MC5. Enable power for the MC board, which is that controller board here. Again, right now it's done on a power supply, but there might be some other setup later down the line. And then in order to see if the MC5 is up and running, you can go to command prompt and just send a ping command continuously. And once the MC5 is booted, then you'll just say response received and all that. All right, there you go.
Yeah.
So now you can actually open up a putty session. The host name. This is all part of like setting up the network adapters. Yes, this address is provided by is configured by the MC5, but also you need to make sure that the PC that you're on has the right network adapter configurations, and there's like a ton of documents and context pages on that. Open up your putty session, and for the current state of the system, you log in as root, and password is also root.
Okay.
From here, just run MC5. If the software is already built, then just run MC5exe and confirm that towards the end that init actually completes. And then you can use all of your LabVIEW utilities like connect, load the right CAL file, set up, and start. Yeah, that's where we left the system off right now. Because I didn't have any of the alignment routine things enabled in the start procedure, because I didn't have the start option. It's just exactly how we left off. It's not going to run anything extra.
And in here you have the scanning process, and one type of the scanning process, the circles that you were doing, or that's a Python?
That's the Python. That's a Python thing. So the way that I had it, so you need a free space connector service that's running, which runs the network proxy to the MC5.
Yeah.
So this needs to be running,
Okay.
and then you just run this Delta RAM suite.
Delta round suite. Okay.
Yes.
You mentioned that you also moved the diagnostic tool from LabVIEW to Python, or was it this the RAM suite? Because you were saying
No,
that,
no, no.
that you were
It's,
trying
it's
to move
I would say just there's a bunch of tools that I had built, but
Uh-huh.
haven't really used that much.
to okay. Just
I don't.
mostly the
Yeah,
RAM
this was a
suite
pretty
and-
recent thing, but where is it? Where is it? Yeah, so this is like sort of like an equivalent to that. You can continuously add more and more to this. It's really, really easy to add to this.
Sure.
But it has the basic things like start your system, stop your system. You can open up the image stream app from here, which again is also just the image. It's the same. It's the same thing as before. You still have your camera ROI stuff.
So it's
and
the
then-
image stream tool that you duplicated from LabVIEW to Python.
Well, this is supposed to be also a duplicate
all
of the other.
everything. Okay.
Yeah.
Okay.
So you
Everything included in one application. Okay.
well, you can also build completely separate different
Sure.
apps because, like, for example, if I don't want that anymore and I want to run like this is just it's the same grading readings. It's implemented as a separate app, mostly for like window flexibility, so you can just like um, but yeah, I would just say that like this Python again, part of the reason why I wanted to do all this in Python was because Python is a much easier playground or sandbox to manage. So you can build whatever you want. Like I also don't think that any of these apps have to stay the way that they are. Like these are really at this point just for my personal use. No one else uses it. So like it's like I would say like anything that you think should be done better should be improved and should be edited and changed. So
Can you open again the RAM application? Oh, wait.
do you want to see
Just to see the user interface. If there is something else that I would like to ask, like I don't know if you need to load something.
okay, so just running because it's a script, it's not an app. So it's not but the interface looks I'm not going to run it mostly because it'll actually move it.
okay.
But this is it's just displaying this graphic. Like
Okay,
there's
okay.
there's no like
I see.
There's
I see.
no,
Just a
like,
script,
buttons and
there is
everything.
no buttons. Okay.
Yeah, yeah.
Okay. I see.
so I will
it starts immediately running
yes
into the equipment.
yeah right
I
yeah.
see.
It starts from where you let where like it is currently and it'll just like start spiraling out. So
Okay.
you can bias it, you can move it to if you say like, oh, I want to scan like over here, then you can move the image, you can move your end face such that it starts here and it will start your scan from here. Although again, just make sure that it's still within the actuator's range of motion or you'll start getting really weird stuff. This is here mostly because that is probably either the end face went out of the camera's the camera's field view and it was latching onto some static piece of dust or a weird artifact, or there's still that big glare that we still see, like this guy over here.
I see.
Like for example, if I actually let me just demo that right now. If I say like I want to move this thing. So
I see.
even if so right now with these lighting conditions, even if you had an end face here, the most likely outcome is that it'll latch onto this guy instead. So just be careful. And I think that well, for the most part, if everything's assembled correctly, this usually doesn't come up, but it's something to be aware of. I will say that this is also a big piece of like potential improvement for the image, the correlation algorithm, just because the general robustness of that is pretty important. Like, for example, if you're trying to like closed loop move to some position, and all of a sudden it just latches onto something else completely, it's going to screw up your closed loop control. It's going to like try and move in that direction, and it has like caused some issues before. So
Cool. Yeah, thanks for
yeah, of course.
for
Yeah, any
explaining again.
yeah, any questions or anything like that left? Obviously, like I'll still be here for another 2 days, so I'll be more than happy to answer any questions. Or is there anything else that either of you guys would like to see demoed?
What do you actually give people? Like Chuck comes over here and says, "Hey, can you test this?" And then you do things and give him
Usually,
check mark or-
usually it's this. Usually it's these values, these SNR values, so the best alignment that you can get. And then another part is basically just using the actual contour application and seeing if you can get error-free shape. And another thing that I do sometimes is, because like, you know, how big this reflection is, that's like an ongoing investigation. So sometimes you want to see like how the rest of the system is doing this, like despite this reflection. And this reflection can be big enough sometimes that it triggers the firmware errors. So you might want to like disable that firmware error bit very specifically, and then seeing if you get error-free shape otherwise. But yeah, so most recently, that's something that I do. Another thing that I do right now is whenever we have a new actuator build, I run backlash testing for that. And that's just a part of, I currently have Python scripts for that, which is just, it's that free space connector testing auto pipeline that I talked about yesterday, but it's this test here, and you just run it as a Python module. Yeah. So the way that
if you run it as Python module, what inputs do you provide? Like a specific number of positions, or
that's defined.
or you just
Here?
call it and that's it? It's everything there, like it's specified.
Well, I mean, you can modify the parameters and everything. So
Sure.
like right now, basically what for this backlash, I'll explain the backlash testing a little bit. But the point of the backlash testing is, let's see if I can.
Okay.
So that's not a. So this is a pretty good representation of the backlash testing that we were doing, but the way that that works is that the whole idea of backlash is that if you preload, let's just say like in the simplest situation, in the trivial case, which is if you have a linear actuator and there's some backlash in the gearbox, what you'll end up happening is, like, say if you tell it because there's some backlash in the gearbox, if you tell it to move forward 10 microns, and then tell it to move backwards 10 microns, that backwards move, it has to overcome the backlash in the gearbox. So it might move like 9 microns instead, or like 8 microns or something like that, but never overshoot, right? So part of that, but that's like the trivial case. Part of what we're trying to do here is to like evaluate kind of the general impact and magnitude of the backlash for the Delta system. And the way that, because we don't currently have absolute encoder measurements of where the actual motor positions are all the time, and plus there's two different sources of backlash in the Delta robot. One is in the motor gearbox, and the other is in like the actual mechanism itself. So like how the joints are like are assembled, and there's like slop in there, and but because we don't have absolute encoders, that's all just like one general backlash phenomenon. And the way that we monitor that is basically if you tell each one of the legs to move a certain number of steps and then you move it backwards, you can basically see from the image, so the X and Y image, the end face image, like how far your end face moves for each of these corresponding moves. And what you can actually do is grab a bigger piece of paper. Basically, the idea is that you have some, and for this, we're assuming that the rate, the in the space that we're testing, that the actuation is like more or less linear behavior. But if you see like the x-axis is like your open loop input command for your motors, right? And that could be one of your legs. Let's just say like leg 0. And then the y-axis would be the absolute magnitude of like how much the image is moved. So like image delta. Right? So this could be in like pixels. In an ideal world where there's no backlash, and assuming linear behavior, you would get a perfect linear line that starts exactly at 0, 0, and that just like depending on, so like if you can think of each of these data points here as like an independent test of like moving it forwards and moving it backwards, and then checking the magnitude of this backwards move. In an ideal world, you would get a linear line that looks like this. But what actually ends up happening if you have a backlash, if you have backlash in your system, is you get something like this, where this guy here, so if you move, this is a certain threshold. This is your x-axis intercept. If you give the motor any input command that's lower than this threshold value, it's just not going to move like at all when you return it back, because it doesn't overcome the backlash like at all. So if you can plot out this plot or this line, you can generally estimate how much backlash is in the system by basically looking at the intercepts of this graph. And then that's what I'm trying to do here, which does show what we wanted to see, which is like that, at each of these step sizes, the move magnitude, that there's some positive x-intercept, there's a positive x-intercept, but there's a negative y-intercept. But so this kind of like tells you how much backlash system for this very specific actuator. I will say though that this test is pretty finicky in that it requires very high illumination quality. As in like your image, because like the way that we actually tell how much something is moved in the image is through that image correlation algorithm. And if there's too much noise in that measurement, then this kind of goes bonkers, which is I think what happened here is actually not bad either.
Those plots are to sub-pixel.
Yes. So what you can do is that the image algorithm is actually supposed to be subpixel, but right now because when we were working with it, it was just the image quality is so poor that we don't get the subpixel accuracy. But usually what I do is I can take like depending on how fast you want this done, you can take any number of images or measurements and then just average them, and then get a decent approximation of where it actually is. And that's what I did for all of these. I think I averaged like 5 or 10 images or something, or 5 or 10 measurements of the image position every time I needed a position. So yeah, that's the backlash testing that I run. What else is there? That's all that I can think of. Again, like for the past 1 or 2 months, a lot of my day-to-day for this project has been bringing up the units that have been built and doing actuator. So I'm sure that will change soon, but
We were talking about the hysteresis.
hysteresis. Yeah, hysteresis is.
Do you do some testing about it or not?
There's a live. I haven't migrated that to.
Is it related with the backslash too?
It is very much related to the backlash, but the general. I have Confluence reports on this as well, but like the idea is that you move, like the actual trajectory of a move is state dependent, right? So if you move from like some 0 position, and then you like do a bunch of like, let's just say like along one single axis, like you just move one axis 100 microns at a time, and this is your end effector. This is your end effector position. But if you like do it backwards, it might look something like this. So it doesn't follow exactly the path.
Oh, I see. I see.
And this is basically what where history shows up.
Okay.
Is that like
It is too bad if it's expanded.
right? So technically,
You get at
The-
the same position.
so the motor positions for this point and this point are exactly the same.
Okay.
In that, like, you moved 100. Let's just say like this is 1,000 microns. You moved this one leg 1,000 microns, and you held all the other legs consistent. And then you moved 100 microns, and then you moved back 100 microns. The output positions of your end effector is completely different, and it's completely dependent on the history of the moves. So like whether or not you did a backwards move, a forwards move, or something like that. But that's how hysteresis shows up in our specific actuator. I think this is not as bad of a problem in the sense that like the places where hysteresis really shows up is when you have really long moves. And the only time when we do really long moves is if we do an image-based alignment, which is like, which is the starting step of like, your image starts here, and then you have to end here, and how do you like closed loop control that? But because that's all in a closed loop, you can actually the hysteresis gets corrected automatically. But backlash is a much bigger issue because it affects the really tiny fine scale moves that we need to do for the thermal drift corrections and all the high speed corrections that we do for active alignment. It also affects the quality of like the signal based optimization that you do here. So backlash is kind of the ultimate metric that we're mostly building towards. And obviously backlash itself contributes to hysteresis significantly. So
Hysteresis is probably just backlash on the other entities.
it is definitely part of that. So but it is also tied with again like the mechanism itself and how much slop there is in backlash, right? So yeah, I like hysteresis is a good evaluation metric for how an actuator is performing, but it's not as high risk as backlash for our specific uses. So I know that Graham has a very specific backlash metric that he's trying to achieve with the actuator builds, and Mark helped develop those metrics. So I think well that's that.
Sounds good. Yeah. So right now, this session is on his profile. I mean, he access to his profile, Windows profile in here in this desktop. I don't know. I mean, when he's gone, yeah, his profile will be maybe deactivated or something like that.
So all of this is on the C drive. You should be able to access all of these
In Contour. Okay.
from any user profile.
Okay.
It's just that, you know, while a user has stuff logged in as like a play session for like their the CMI process and things like that, then another user might have trouble getting that running without breaking stuff. So, but yeah, so all this stuff is 100% runnable from just the different user profiles.
And the updates that you did are committed already in the Bitbucket repositories or in the SVN? Like,
Yes,
is there
I think
any
so.
major
I'll make
changes that you
I'll,
need
I'll make sure that
to commit?
I'll make sure that everything else is
Okay.
committed.
Mhm.
Like at least in terms of like, for example, this repo and then the MC5 source code. There hasn't been a lot of changes, but I'll double check.
Okay, perfect.
Anything else? No. Okay. So my plan is later today I'm gonna like publish a version of like the open items like Confluence page that I've been working on, which is like all the stuff that I think could use work on or like I'd be concerned about. I would like you guys to maybe get your eyes on it and just to read it through briefly and then see if you have any questions.
Sure. Mhm.
For any comments.
Sounds good. Mhm.
What's that? We got like pretty good SNR on that, like 21 dB, 20 dB. I think so. Yeah.
So you mentioned that you opened the files from the NCF5 in here, and it's gonna happen this session or folder that you open in your profile here. It's gonna be also available in the Contour, and
What do you mean?
because when you were working with the code, you were saying that you were working with the real code that is existing in the
Yeah.
CPU of the NCF5, that you open it here in your user, right? Is it gonna be available in the Contour? I mean, you should be able to set it up, right? Or
Contour, the LabVIEW application is on disk on that PC,
Mhm.
gone toward the embedded application.
Yeah,
is
yeah, yeah. It's already.
MCFI.
But should we open a session to?
Anybody can access the MCFI. Like you said, it's a Samba server, so you just go to that address, and on your profile, you go to that address, and you'll open up the MCFI source code. You can
Okay, yeah, you're right. I need to write this, right?
Yeah,
Uh-huh.
that's common. You can just ask me.
Okay.
Embedded team.
Okay, okay.
And then the LabVIEW application also is on, SQL and
Sure.
source or
Mhm.
whatever anybody.
Yeah, so anyone from software team also Chuck can help you a lot with that. But this like this network address here just maps to, or at least when you're using the Samba server, it maps.
Yeah, to all the files that are in there.
Let's see, first, like this is this folder. You can see like this is the same.
Interesting.
That's where the Samba.
Okay.
I've got a Confluence page on how to get Bitbucket credentials, how to log into the MCFI, how to build the MCFI software, all that stuff.
Okay, if you can share that to me, yeah. Thanks. Mhm. All right.